Welcome you to this series of lectures on marine hydrodynamics. Today we will talk about give a brief introduction to water waves, and in the subsequent lectures we will talk in detail about water waves. Basically, when it comes to water waves, like many other waves, we have when it comes to before going to water waves, let us just talk about wave. What I mean by wave and where it occurs. When it looks at waves, it is a propagation of energy in a medium, and it is like we have for mechanical waves we need a medium like waves in a solid, vibration of a string or vibration of a membrane or a beam vibration, that is a waves propagate, that is a wave that propagate in a solid. On the other hand, when you look at the energy, that is the electromagnetic waves, then in that case it does not require any medium, X-ray waves, and we have light waves. So, these are kind of electromagnetic waves. On the other hand, when you look at waves, as I told you, the vibration of a beam or a string, or even if in the sound wave propagation, acoustic waves, then we have these are kind of mechanical waves. A similar such wave is the water waves. The theory of water waves, in fact, is a more general one compared to any other wave, and in fact, it was told Sommerfeld gave this statement. Sommerfeld told, is a well-known physicist. What he suggested, he told that in fact, the theory of water waves is a general model compared to, is one of the most general model of waves compared to all other waves. So, as I have told in my previous class also, the water wave is one of the most general type of waves. So, once we know the theory of water waves well, or the various phenomena associated with water waves, there are it is easily other waves, the similar concept or similar methodology can be used, or this methodology can be borrowed to deal with other waves. And in the last 150 years, there is a significant progress in the development of the theory of water waves. A major part of the theory of water waves is based on the assumption that the fluid is inviscid, incompressible, and motion is irrotational. However, the complexity comes from the free surface boundary condition, that is, here on the free surface boundary conditions are highly nonlinear, and that makes the problem more complicated, even if the assumptions on the fluid is very simple. That means, even if we deal with a potential flow problems, the free surface boundary conditions which are highly nonlinear makes the problem complicated. As a result, very few problems of the general model of water waves can be handled for solution, and still large. So, in the process we again go for idealization of this general theory, and in the process several theories have come up to deal with the problems of water waves. In this we will start with a very simple linear theory and understand some of the phenomena of water waves, and afterwards we will give, because we will just discuss in brief about the some of the nonlinear waves. So, when it comes to the theory of water waves, first of all we need to know what are the various types of wave. As I have told you that in case of a wave propagation problem, there is a transfer of energy which takes place, and most very often in a periodic interval the pulses change with a certain periodicity. So, if I look at, suppose I have a one of the simplest wave is the sinusoidal wave. If I just say eta is equal to a cos k x minus omega t is the most general representation of a surface. And if I say this surface is a V surface, then I call the, suppose I take this region, then this is the total distance, I call it as lambda. Lambda is called the wavelength of the wave, and then is the amplitude, and then we have k is equal to 2 pi by lambda, which is called the wave number, and t is the period of oscillation, time period, and then c is lambda by t is called the phase velocity or wave celerity. Then we have another factor in case of, if h is the depth of water, then we have other factors like this point, the maximum highest point is called the crest or peak, and this is called the, these points we always call this as the crest, this is the trough. So, when once it completes one complete from here to here, this is called one complete cycle, and then we call a complete one complete wave. Again from here to here, this is another cycle, we call this another wave. It's complete one cycle complete. So, if this to this distance we call the lambda, and the time covered by the wave to propagate from this to this distance is called the period, and c is becomes the phase velocity, which is lambda by t. And some of the other, h is the depth of water, then what will happen, h by lambda, we call this as the relative depth, and we have again we have omega is the frequency, called the wave frequency, then we have omega is equal to 2 pi by t. Then we have another factor that is called h by lambda, that is called the wave stiffness. So, these are some of the parameter. Eta is the surface elevation, and this is one of the very simple sinusoidal cosine wave. Then some of the other waveforms, some of the simplest other waveforms, if I write eta is equal to, in fact we can call it plus minus a sin k x plus minus omega t. Similarly, we can also have in the combined form the exponential form e to the power I times k x minus omega t. So, in this one, if you look at the real and imaginary parts, both of them will represent waves. Real also will give us the sine and cosine waves. So, with this, then what is another thing which is important in the, which will derive later, but let me first introduce that there is a relation between omega square and k, omega and k, that is omega square is tan g k tan hyperbolic k h, and this is a relation. In fact, for almost all waves such a relation is exist, and that relation I call the dispersion relation. And this dispersion relation, where it is a relation which always relates the frequency of the wave with the wave number, and in fact what will happen, this relation gives lot of information about the wave characteristics. Then often if we know the period of the wave t, we know, then we know the omega. Once you know t, we know omega. Then if we know the water depth h, if these are the things which are known, this is also known, one of them is known, then what will happen? Can we find k? Then k is equal to what? So, in fact, we can easily find out what is k by solving this relation, and once we find k, once k is known, we can always find what is lambda. Lambda is nothing but 2 pi by k. So, this dispersion relation, I will come to the detailed derivation of this relation a little later, but today let me emphasize on this. Then particularly this we are looking at as if I have a depth of water is h, the water depth is h, I have any wave is propagating on the surface. If I say y is equal to eta x t in the surface, then we have this is the seabed, assume that it is a uniform water depth, depth is uniform, then what we have, then what will happen, this is called the y is equal to eta, y is equal to eta x t is the free surface, and then this line, let us suppose this line is the x axis, and suppose this is negative direction is the downward direction is the, then I call this as y is minus h, then this is line y is equal to 0, this x axis is nothing but the line y is equal to 0, then y is equal to 0, this line is called the mean free surface. Or still water level. And there is no wave, y is equal to 0, and it is the still water level, and when there is a disturbance, then we call y is equal to eta as the free surface. In fact, as I have mentioned that on the free surface this eta is not known, eta is not known. What is known? Pressure at surface at y is equal to eta, the free surface is the atmospheric pressure. So that means on the free surface the atmospheric pressure is known, which is atmospheric pressure can always, but this surface, so this surface is a very dynamic surface and which is not known. So always we need to obtain what is the surface, one of the major problem associated with the waves. Then another thing, if I again look at this dispersion relation, then I can easily find what will happen when h is large. When h becomes large, when h is large, then I will have omega square is equal to g k, because tan hyperbolic k is initially, and this becomes g k for k large, h large, then that becomes omega square is g k. So that what happened, it gives me that this becomes the case of deep water waves, deep water. So this omega square is g k deep water dispersion relation. So now we will define what is the classification of the waves. When you look at the classification of the waves, we comes across two things. As I say, the h by lambda is the relative depth, relative water depth. If this is the relative water depth, then what will happen here? Then if h by lambda is greater than half, then we call this deep water waves. On the other hand, when h by lambda is less than 1 by 20, we call shallow water waves. On the other hand, when 1 by 20 is less than h by lambda is less than 1 by 2, we call these waves of intermediate depth. In fact, there is a large class of problem where we always come across either this case or this case. We had the recent Japanese tsunami, or 2004 we had the Indian Ocean tsunami. In that case, tsunami always is modeled as a shallow water waves, although maybe in the deepest in the ocean, but if you look at the wavelength and the period of the waves, then compared to the, if you look at the relative water depth, always you will see that this is a shallow water waves. So, many such waves exist in the ocean, that is like let me just briefly say what are the various types of wave that all exist in the ocean. You know, we started acoustic wave, then we have capillary gravity waves, we have ripples, we have wind waves, inverse load, and then we have gravity waves, then we have the tsunami, we have storm surge, then we have tidal waves. Now, the tidal waves, I mean always astronomical tide, because often astronomical tides we have planetary waves. So, if these are the various types of wave, always the question comes, what is the typical period of these waves? If you look at the period of these waves, wave period, the wave period of a wave, depending on the type of wave and the nature of wave, it can vary from few seconds or part of a second to few days. So, like you look at, suppose the acoustic wave, it is in a very small, the period is very small of a second, whereas capillary gravity waves, the ripples, they are in seconds, these are all waves which are in seconds. But you look at tsunami, storm surge, they are in hours, tidal waves, it is in hours again, and then planetary waves, it is in days. So, if you look at the details, one can find from the books of CCMI, Applied Dynamics of Ocean Surface Waves. Of ocean surface waves. There it has very nicely described the various types of waves, the restraining forces acting on it, and what is the typical period of these waves, and where they occur and how they occur. So, I am not, I will just briefly say. So, when we have seen that we have in general we come across three types of wave, then what will happen to the, because we have a dispersion relation, we have seen that we have a dispersion relation, that is our omega square gk tan hyperbolic kh. So, if I say that kh h by lambda is greater than half, which implies what will happen to this? It will give me, then we have what will happen implies kh will be sorry h by lambda. So, if I put it lambda is 2 pi by k, okay, h lambda is 2 pi k, that is greater than half, which implies kh is greater than pi. If kh is greater than pi, one can see that tan hyperbolic kh tends to 1 as kh is greater than pi. Then in that case, we will see that our omega square becomes gk, and this is basically the case of deep water waves. In a similar manner, we can see that when kh is less than pi by 10 in the, then we have tan hyperbolic kh becomes kh because it is small, and then in that situation we have omega square is gk into kh, which implies omega square by k square equal to c square, which is gh, which implies c is equal to root gh. So, this is another relation. So, this c is equal to root gh is the, c is nothing but the phase velocity, c is rather we have seen that our c is equal to lambda by t, which is nothing but omega by k, and that is the phase velocity, the rate at which, and this happen when kh is less than pi by 10, that means it is same as h by lambda is less than 1 by 20, whether this or we say this. That means it is the case of shallow water. So, in case of shallow water, we have seen that the c in case of shallow water, rather for shallow water, we have c is equal to root gh, and c is the speed up at which the wave propagate. That means the speed of propagation in case of shallow water depends on the just the water depth. In fact, in the tsunami travel time chart, we always, one can always observe that the tsunami travel time chart is based on this formula. You want to know the time taken by the tsunami waves to propagate from the deep sea to sea, always this formula is used, although this is the formula which is often used, the one of the simplest formula. However, there is a proper the depth the depths are calculated or taken at various points from observational data. The water depths are fixed, taken at various locations are initially obtained, and then knowing the water depth at various location, then we always find how much time it will take when a tsunami occurs at a particular. Even if you look at the average, just to get a just to have an idea of what happens. Suppose if I say my water depth is 4 kilometers, which is a kind of average ocean depth, and I just say if it is 4 kilometers, then my c speed of propagation will be 4000 to 9.8 whatever, which I can just roughly say meter per second. We cannot say 4000 into, if I put it as 10 just roughly, which can be equal to 2200 meter per second. So, it shows that if I am dealing with a shallow water case, where c is root gh, and the depth of water at a point is 4 kilometer, which is the average ocean depth, then the speed of propagation will be 200 meter per second. But what will happen if the same wave, when it propagates to the shoreline, when the water depth h decreases, then I will say that speed of propagation c will decrease. So, the speed of propagation decreases, but another question comes, what will happen? Of course, here I have assumed there is no changes in the other phenomena that is associated with it, particularly Soling, reflection, refraction, all these things. If I say that is not taking place, then there are various phenomena associated with these kind of waves. I will come to that later. But then, so similarly, if I look at another aspect, that is in case of a deep water, in case of deep water, omega square becomes g k, and this is k, omega is 2 pi by t square, g 2 pi by t, 2 pi by lambda. So, which implies, so 2 pi, this 2 pi will go, that will give us, so that will another 2 pi only will remain. So, 2 pi by t square g by lambda, which implies lambda is g by 2 pi to t square. So, that means here it says that in case of deep water, lambda varies as a t square. If the period increases, lambda varies as a t square, because g is a constant, 2 pi is a constant. So, that means wavelength will increase with increase in time period. So, larger the wavelength. So, these two observations has told these two cases. Here the depth will decrease, h decreases, c will decrease, speed of propagation will decrease. On the other hand, with increase in time period t, the wavelength of the wave will increase, because lambda varies as t square. Now, with this understanding, now let us have a look at the general nature of the waves. When it comes to wave, if I have a surface, any surface, if I say eta is a function of x t, which y is equal to eta is the surface, then what will happen to eta? It has to, if it represents a wave, that means the surface eta, the free surface, and this eta has to satisfy del square eta by del x square is 1 by c square del square eta by del t square. So, anything which, when a moment I talk about wave, I should have a surface, and that surface has to satisfy this relation. This is the case of a one dimensional wave equation. Similarly, in case of two dimensional wave equation, we have del square eta by del x square plus del square eta by del y square is equal to 1 by c square del square eta by del t square. In this case, I consider my surface is a function of eta is a function of x, y and t. Now, if you look at the general solution, let us take the simplest one. If I look at the general form of solution, because eta, then the solution of this will be in general of this form, eta x t will be f of x plus c t plus g of x minus c t. This is the general pattern of this solution. Any, because here this is a partial differential equation. So, the second order partial differential equation. So, its solution will be some arbitrary functions, unlike in case of a differential equation where the solution will come in terms of arbitrary constants, but here two arbitrary function f and g, but the general pattern is f of x plus c t x minus c t. So, when we look at eta is equal to a cos k x plus minus c t, or we say eta is equal to a sin k x plus minus c t, or the general case exponential form, like you have e to the plus minus I k x plus minus c t. Then all these forms they are one of these particular cases of this form. So, they all represent then, and this in this form, this is the wave which propagate in the negative direction with velocity c, and this is the wave which propagate the positive direction with velocity c. So, that is what. So, similarly, so when we think of waves, we have to always think of two things. One is the direction of propagation, because that is very crucial, and another factor when we are looking at waves comes is various phenomena associated with the wave. In fact, the various phenomena associated with the waves are the reflection, transmission, scattering, diffraction, refraction, soling, etc. These are the various phenomena. So, in fact, it is not only that, it is not only then we have radiation, it is not only that only in case of light we have some of the phenomena, but any wave, the moment we have a wave, we have all these phenomena occurs depending on the type of waves, type of medium, some of the particular phenomena which dominates, and this is what will be coming here also in water waves also. All these waves, all these various physical phenomena exist, and it all depends on the type of problem we are looking into, or the nature of obstacle we are looking into. Depending that, we always define what kind of wave, what kind of phenomena it will be associated with. Now, because in the next class, although I will come in details about how the theory of water waves is developed, but I will just here, since I have taken I am considering this as a very brief class. So, I will consider some of the very basic characteristics of the water waves, of the waves in general. Suppose I have a wave eta is equal to a cos. I will come those things in detail about water waves theory in the next class. Suppose I say eta is equal to a cos k x plus omega t. This is a wave which is propagating in the negative direction, and suppose I have another wave eta, and let me call this as eta 1, eta 2, another wave eta a cos k x minus omega t. Then what will happen to the resultant of these two waves, eta 1 plus eta 2? Then this will give us 2a cos, this will give us 2a cos k x cos omega t. So, this is a, so there are two waves, the same wave, the amplitude of the waves are same, whereas the wave number, frequency, everything is same, only they move in the opposite direction. Then what happens, the resultant wave becomes, these are all progressive waves, whereas the resultant wave is a standing wave. And unlike the case of a progressive wave, the standing wave we always see the formation of nodes and antinodes. These are the antinodes, these are the nodes, this is also node, and we can see that the excitation of the particle here, the horizontal excitation of the particle is highest, whereas at this point the vertical excitation of the particle is highest. So, this will come in detail. Rather, suppose what will happen here, I have taken the two waves of the same amplitude, but if I just look at the two waves of different amplitude, then what will happen? Then what will happen to my eta, which is a combination of eta 1 plus eta 2? this will give me A1 plus A2, A1 plus A2 into cos kx cos omega t plus 1 minus A2 sin kx sin omega t. And if you look at this, so if you look at the amplitude of these two waves, the maximum amplitude A max will be A1 plus A2 and A min will be A1 minus A2, provided we assume that A1 is greater than A2. Then what will happen? Then what will happen to A1? A max plus A min by 2, and whereas A2 A max minus A min by 2. So, that means if I know and how this wave pattern will look like, this is the mean free surface. So, this is the type of that is the way the wave will propagate. So, this will be give us here the maximum amplitude, and at this point it will be the minimum amplitude, whereas this is the still water level, this line is the still water level. So, what happen often when you look at the tank, a wave initially you have a wave which was propagating in the positive direction. Then if this was initially this wave was propagating in the positive direction, it come across a wall, and after meeting a wall it get reflected, vertical wall particularly I here say. When it get reflected, the resultant wave is this wave, which is a turning wave, and this turning wave, then what we see, we always see the surface of the wave, that is the this becomes my surface of the wave, and this wave is what I call this is a Clapeyron, partial Clapeyron. That means all a partial standing wave. And when they become same, then we call it a complete standing wave. And in fact, in the earlier days, the ratio of the amplitude of the incident to amplitude of the reflected wave, that is A2 by the amplitude of the incident wave, that is A1, and which gives me, we call this as Kr, that is the nothing but the reflection coefficient. This reflection coefficient, and then if we look at this becomes, this used to be obtained by using this formula, A1 is A max plus A min and A2 is A max minus A min. So, always this distance used to be measured, this distance used to be measured, and because this is the A min minimum amplitude A min, and this is the maximum amplitude. So, near a wall, to always to know what kind of wave that is formed, what is the reflection coefficient of a particular wall, this formula was used A2 by A1, where A2 is nothing but A max minus A min by 2 and A1 is A max plus A min by 2. So, that is one way of obtaining reflection coefficient of a wave. Another simple things here, see, we have just seen that how by changing the amplitude of the waves and direction we are able to. Now, if we look at not only amplitude, what will happen if I just say that we have waves of similar nature propagating in the same direction. Suppose I say my eta is a combination of A1 cos k x minus omega t, all waves are propagating cos k x minus omega t plus 1 only the amplitudes are changing, then it will be A1 plus A2 plus An plus 1 into cos k x minus omega t. So, it is like as if we are just, if similar waves they are of different amplitude, they propagate in the same direction, then only the amplitude changes. But what will happen? What happen in the ocean surface? We always see the ocean surface is a combination of waves which are of different nature. So, it may be A1 cos k x minus omega t, then another wave k 1 x omega 1 t, we may have a eta 1, this is eta 2 A2 cos k 2 x minus omega 2 t. Similarly, if you go on like this, so we may have eta n is equal to A n cos k n x minus omega n t. Then we will look at the total resultant, eta is equal to eta 1 plus eta 2 plus eta n. Then whatever pattern we get, it becomes sigma A n cos k n x minus omega n t, and this wave, although they are sometimes originated from regular waves, all are regular waves, but the pattern of the sea surface, what we see when we combine all these waves, it need not be, surface need not look like regular, because the combination of these waves will give us a very irregular pattern. But it may happen that all these waves are originated from the individual waves. So, that is what we see when we look at the sea surface. Then suppose I will just tell, see, these observations may be very simple, but these observations are very important while analyzing the various problems related to water waves. Suppose I say eta 1 is equal to A cos k x minus omega t plus epsilon 1, and I have eta 2 is equal to A cos k x minus omega t plus epsilon 2. Then my resultant wave will be, then what will be my resultant wave? Eta will be eta 1 plus eta 2, and if I just take it, which can be, let me look at two things. When epsilon 1 is epsilon 2, if epsilon 1 is epsilon 2, then my eta, which is the resultant of the two waves, this will give me 2A cos k x minus omega t plus epsilon, because epsilon is equal to epsilon 1 is epsilon 2. On the other hand, if I say that epsilon 1 is 0 and epsilon 2 is equal to pi, then what will happen? Eta 2, eta, the eta will be, this will be A cos k x minus omega t, and epsilon 2 is pi. So, this will be minus A cos k x minus omega t, and that resultant is 0. So, here the amplitude, just to look at the phase change, this is the phase, there is a change in the phase, and because of the, if both are of the same phase, then the amplitude is becoming twice the that of the individual waves, but if they are 180 degree out of phase, that means then the resultant is becoming 0. So, in many situations, engineers always are interested to know that if they want to increase the amplitude of the waves, they can always create a wave. If the two waves are of the same phase, then that will give me the resultant wave, and propagate in the same direction, and the resultant wave will be twice, amplitude of the resultant wave will be the twice that of the individual waves. On the other hand, if you want to nullify the effect of one wave which is propagating, one of the mechanism one has to introduce is to generate a wave, a different wave, whose phase is, who has a, which the wave generate a different wave, and that wave should have a phase which is 180 degree difference than the original waves. Basically, then in that case we can see that the resultant wave is becoming, resultant effect is becoming 0. So, that is another, so there are physical mechanism one has to introduce. So, this understanding of these things becomes very crucial, because that gives us very important information to design different types of structure, so that we can generate or we can attenuate the waves. There are various, in fact, as I have told you that here this in this process where this is two waves of different phase. Now, suppose what will happen, the waves, if the waves, as again we have already seen that if waves propagate in the opposite direction, then standing waves are formed. Again, if you look at the standing waves, then what we will do with these standing waves? If I look at a standing wave, what will happen to the resultant of different standing waves? Suppose I have two standing waves, then of the same amplitude or different amplitude. Similarly, we can say that the resultant will be eta 1 plus eta 2 is equal to a 1 plus a 2 into cos s cos omega t. One can look into similar situations, like when we have again a change of phase in case of a standing wave, then also we will see that a similar observation will happen, because the resultant either will decrease or it will increase, depending on the whether we are considering waves of the same phase or a different phase or any other changes. So, that will also give us some insight to look into problems where we are looking at generation of waves, amplitude, higher amplitude waves or lower amplitude waves. So, with this understanding about the basic understanding about the waves, and as I said that in water waves the basic relation is the dispersion relation. Otherwise, the general nature of the waves remains the same, because here, but in the process another thing here, G is the gravitational constant, acceleration due to gravity. It is a constant, acceleration due to gravity, and here this and this is the dispersion relation. So, often these water waves, so that means because of it all depends on this gravitational constant is a. So, sometimes we call these water waves are the gravity waves. In fact, the very well known gravity waves is the Airy waves. The small amplitude gravity waves, this is often called the Airy wave or first order Stokes wave. So, with this basic understanding about the gravitation, okay, let me just work out another simple example before today's completing today's lecture, because that will give us a very little insight about the various phenomena that is happening. Suppose I have a wave which has a, I just take out an example, because tomorrow in the next class I will talk about how these waves, how this all these things are coming up, and how it has, because I am just talking about waves, but how this is related with the fluid and what it has to do with, because here in case of water wave we have a fluid motion and then we have a wave propagation. So, two things in details I will come in the next class, but here suppose I have a wave, I have a whose the water depth, suppose I say the water depth is 2.3 meter and has a period, I have a wave period, just work out a small example. This is the wave period is 10 seconds. then and I have a wave height which is that is 2 meter. So, if I am been asked to calculate the velocity and length, find the c and lambda, find c and lambda. So, to do that what I will say, I have the water depth is very small. If I assume, because I have a wave height is 2 meter, whereas the water depth is 2.3 meter. So, I must have a wave which is whose depth is similar to the wave height. So, if I assume, I just assume that it is a shallow water, case of a shallow water waves. If I assume the case of a shallow water waves, then what will happen? My c will be root g h, just I have talked about. If c is nothing but lambda by t is root g h, which implies lambda is equal to. So, what will be my c? C is g, h is 9.8, 9.8 into h is 10, h is 2.3, and this gives me 4.75. meter per second. And if I look at lambda by t is g h root g h, which lambda is equal to t into root g h, and that is t is becoming 10 into 4.75, that is meter, that will be 47.5 meter. So, here we put, so by lambda becomes 47.5 meter, whereas my speed of propagation is 4.75 meter. Of course, I have assumed that this is shallow water waves. If whether, let me check whether this assumption is a valid assumption or not. So, if this assumption I have to tell that my s by lambda, what will happen to my s by lambda? My s is 2.3 meter and lambda is 47.5 meter, and this will become 0.48, and which is always less than 0.048, sorry, 0.048, which is less than 0.05, and then if it is less than 0.05, that means 1 by 20. So, this assumption I have taken as this assumption shallow water is justified. So, shallow water assumption is justified. Is valid, but it is not always necessary that I take assumption. If it is not valid, then what, in that case what I have to do, then I have to, in the other case I have to go to this equation, that is omega square is equal tan hyperbolic s. Often what we do, we try to validate this, we always again call it, suppose it is a case of a deep water, and then if this is not valid, if we have to consider the case of a deep water, and in that case we will have omega square is g k tan hyperbolic g k, and in that case again I will apply, because my water depth is there. So, in this case I cannot apply, because what sorry, I have a water depth is this. So, I cannot apply this, because it is anyway no case a case of finite infinite water depth, because my water depth is 2.3 and wave height is 2 meter. So, I cannot apply this result here. On the other hand, if this does not hold good, then I have to directly solve this equation, and by a numerical method like Newton-Raphson method or so, I can substitute for T, H and G, then and I will solve it for the numerically to obtain this, and I request all of you to work out few problems numerically to find how the k is obtained by using the Newton-Raphson method, and always you will find that will be one positive real root, one real root of this. That means, for the moment you have a water and you have certain the water has certain depth, then there is one real root, means one wave will exist in the water, that is what one progressive wave pattern will exist. The moment you have a disturbance, that wave will propagate. So, with this basic background on water waves, today I will stop. In the next class we will concentrate, start from the basic equation of fluid mechanics and try to come out that there is a wave in the water, and the details will come. Although today I have assumed that there is a wave, and assuming the dispersion relation is a particular omega square is equal to n hyperbolic case, certain basic results I have derived, but in detail will come in the next class. Thank you.